In this video, we are taking a look at evaluating limits analytically, right? So we're looking at limits and there's a part of them, sometimes we might have to use a graph, but mainly focused on without a graphing calculator, how do we evaluate these limits? What are some things that we look for? Okay, so first let's talk about direct substitution. What is it? When can you use it? When can you not use it? All right, so direct substitution, you've used it literally hundreds of times before, and that's exactly what it sounds like. It's when you plug values in. So that's plugging values in. Into your function, right? So it's just you're plugging values into your function, and your output will then be whatever your y value is. That's what direct substitution is. And then when can you use it? Well, that's simple. I'm just going to say with most, not all, but most functions, you're able to use that. And part of what we're going to look at today is explore when we cannot use it. And a lot of times what we can't use it is where there are these things called discontinuities, or where the limit fails to exist. Okay, those are examples of when you could not use direct substitution. So let's go ahead and look at some basic limits here. Number one, it's if you're taking the limit of a constant. So the limit as x approaches some value c of a constant. So b here is a constant. Okay, that would be like your function is y is equal to 7, something like that. If you're taking the limit of this function at any value of x, it's always going to be that constant, which is 7. We'll do an example. Like down here, right? So here, this 3 is a constant. So this is the equation y equals 3. You're finding the limit as x approaches 2 of the function y equals 3. It's a constant, and y equals 3 is just a horizontal line at 3. So even when x is 2, right, your y values are always approaching the same value, which is why your limit is always going to be 3. Another case, the limit as x approaches c, of what about if it's just y equals x, or something similar to that? Well, then direct substitution, you are substituting in right there. It's just going to be then y equals, or your constant, your limit, there we go, is just going to be c. Let's do an example. Example B down here is to show kind of what that looks like. In this case, your function is y equals x. And remember, when you're finding the limit as x approaches, in this case, -4, it's just direct substitution. So your answer is just -4. That's going to be your y value, because if you think about y equals x, it looks like this. And as x equals -4, 1, 2, 3, 4. Well, if y and x are equivalent, this 2 is going to be 1, 2, 3, 4. Right there. And then the last one, the limit as x approaches c of x to the n is equal to, this is any polynomial. So the x to the n represents a polynomial. Just directly substitute it, it would be c to the n. All right, so the value of that polynomial, you would just plug it in. For example, if you have x squared, so your function is x squared, just substitute that in, that'd be 2 squared, or 4. And that's it. Pretty simple, right? Sometimes you can just plug them in to find those y values. So now let's take a look at some properties of limits here. So first of all, when we're talking about the language that we're going to speak, there's a few things that you have to understand. So when I say that the limit is L sub 1 or L sub 2, that's looking at the limit as x approaches c. L sub 1, we're looking at f of x, because you notice down here you have f of x and g of x. And then if I say the limit as x approaches g of x, we're looking at, I'm going to say L sub 2. And so those are just those, L sub 1 is the limit for f of x, and L sub 2 is the limit for g of x. And L is just the numerical value, that's the y value for that limit. So to keep those things in mind. And again, down here on the scalar multiple, the b is just a constant. So b, that's just a constant. If you're taking the limit as x approaches c of a constant times the function, now you could think of that as just the constant times the limit of that function. If you kind of want to back up a step, you could think of it as the limit as x approaches c of the constant times the limit as x approaches c of the function, right? And we know that this from above is just b, and the limit as x approaches c of the function is just whatever that limit is. So you get the same thing. However you want to think about it, add this extra step in here to help you understand what's going on. Okay, and that's what I did down here looking at the sum and difference. So again, if you need to pause the video, jot these down, please do. On the sum and difference, if you take the limit of two functions being added together, you can just end up adding those limits together, because you're going to end up taking the limit of f of x, the limit of g of x individually, and you'll end up just, again, adding those limits together. For the product, you're just multiplying those functions together. Well, when you find the limit, you can find the limit of f of x, which is L sub 1, and the limit of, g of x, which is L sub 2, and just end up multiplying those two limits together. And the quotient's the same thing, only now you're dividing them. So it's f of x divided by g of x, so you have L1 divided by L2. And the power. So now this is where you have a function to the power of n. That's just whatever the limit of that function is, or the y value of that function is, to the power of n. All right, so make sure you jot these down. I know there's a lot here, but go ahead and pause it if you need to, and jot these down before you move on. Now let's take a look at an example. So here you have a function plus a function, right? That's the sum and difference property of the limits. So what you could do is you could do the limit as x approaches 2 of 4x squared plus the limit as x approaches 2 of 3. And if we do that, you would plug the 2 in right there. And that would be 4 times 2 squared plus, and this is a constant, so that would just be 3. And so that would be 4 times 4, that's 16, plus 3, which is 18. Okay? And that's using the rule with the sum and difference property up there. And now let's take a look at limits of polynomial and rational functions. In a bit, we're going to get into the question of what happens when you can't take the limits. But now let's look at a couple more examples of what happens when we can. What does that look like? For here, we have a rational function. And first thing you do is direct substitution. So let's directly substitute this in for all of your x's. So you'd have 1 squared plus 1 plus 2 all over 1 plus 1. And when we simplify that, that gives you 4 over 2, which is just 2. Okay. Now if a limit has a radical, I don't have an example here, but I'm going to give you an example. So let's say you have the limit as x approaches c of the nth root of x. Well, again, you're going to just directly substitute that in, and that would give you the nth root of whatever that c value is. Okay? Now, let's take a look at, we're going to take a look at some radicals, but we've got to talk about this idea of a composite function, right? And so if you think about what a composite function is, it is a function that's made up of more than one function, just like in geology, which rocks, by the way. But geology, it's made up of, there are rocks that are made up of more than one kind of sediment or more than one kind of rock, and those are called composite rocks. Right? It's the same thing in mathematics. We use the same similar words to explain the same idea. And with what that looks like in math is this f of g, or I like to use this a little bit more often, f of g of x. But they mean the same thing. All right, so now let's take a look at composite functions. Go ahead and try these on your own. Pause the video, try these on your own, and then come back to see how you did. All right, so for the first one, you have the limit x approaches 0, and again, we're just going to try directly substituting this in. So you'd have the square root of 0 squared plus 4. That gives you the square root of 4, which is just 2. So it works. And when you try this other one, you're just substituting that in. You'd have the cube root of 2 times 3 squared minus 10. 2 times 3 squared, that's 2 times 9. So that would be then 18 minus 10. So the cube root of 18 minus 10. And then when we look at that, that's the cube root of just 8, which is then 2. All right, so that one, they both, in this case, simplify down to 2, or the limit as x approaches those x values is equal to 2. All right, so now let's take a look at some trigonometric functions and their limits. Now, all of these are it's pretty straightforward. So if you want to just pause the video right here and get these jotted down, I don't have much to say about them because you're just directly substituting. That's all that it is. Okay, so pause the video and write them down. So now we have all of these. We have the limit x approaches 0 of tangent, and then x cosine of x, and then sine squared of x. Go ahead and find these limits. Pause the video, find these limits, and then come back and see how you did. Okay, so let's see how we did here on A, the limit as x approaches 0 of tangent. You plug in your tangent of 0, right? And remember, tangent of 0, you might have that memorized, but it's just sine over cosine. So sine of 0 over cosine of 0, so that's 0 over 1, which is 0. Over here, on part B, plugging in your pi for your x and your other x. So pi times the cosine. Cosine of pi is -1, so -1 times pi is negative pi. And then on the last one, the limit as x approaches 0 sine squared. Well, when we plug that in, right, sine of 0 is just 0, so 0 squared is also just 0. Now let's look at a strategy for finding limits. Because sometimes, like on this one right here, let's look at the function. The direct substitution doesn't work. So if we plug in the 1 there, you notice you'd have 1 to the third minus 1, which is 0, and that's fine. But over here, 1 minus 1 is also equal to 0. So you can't do that, right? There's no solution there. You can't divide by 0. And so we have to look at other ways to solve it. One of those ways, this is the last ditch effort, is to look at the graph. So here's the graph of that function. So as x is approaching 1, that's right here, we're looking at the y value. So about right here, if you look straight over, your y value is at about 3. So we know that the limit is 3, but since it doesn't have a y value there at x equals 1, we can't use direct substitution. So we're going to explore other ideas or other ways to do that. So the first strategy that I have would be just try direct substitution. That's the easiest way. That's the way that most often is going to be successful for you. So try direct substitution. Then, if that doesn't work, we're going to do some examples of rewriting or just trying to see if you can simplify it in some way where you can plug that bottom value in or that limit into your function. And then the third way is to look at the graphs or tables that are associated with that function. All right, so copy this down and then we'll move on to the next problem. So here's one. If we try plugging -3 into here, you notice you get 3 squared plus 3 minus 6 all over negative 3 plus 3, and you get something over 0. It doesn't matter what the top is at this point. But it's over 0, so direct substitution fails to exist. Now what we have to do is we have to rewrite it. In this example, we're going to rewrite it so that stuff cancels. Notice the top is a polynomial, which is quadratic. It's a quadratic polynomial, which can actually be factored. So go ahead and factor that, see what happens, and then try resubstituting the negative 3 in. Go ahead and pause the video, try that on your own, and then come back. So here we see that if we factor the top, you get x plus 3 times x minus 2. And that works perfectly because the x plus 3's are going to cancel out. So you have this x plus 3 and that x plus 3, they end up canceling out. Then you rewrite the whole limit. So now the function has changed. We've simplified it. Its limit is x approaching negative 3 of x minus 2. And then you directly substitute that in, you get negative 3 minus 2, which is then negative 5. So this is your y value. If you were to graph this function, it would look like the function x minus 2. It would look like that function. It would just have a missing value at x equals negative 3. And let's go ahead and try one more. Okay, now let's take a look at this one with rationalization. So we're not simplifying it like we did the last one, we are rewriting it. We're reconstructing the function so that it looks a way that we need it to look, because if you try to plug in 0, you would have 0 on the bottom, so we can't do that. So let's try rationalizing the function. And by doing that, we're going to multiply. So let's rewrite it. So x plus 1 minus 1 all over x. We're going to multiply it by x plus 1 all over the square root of x plus 1 plus 1. All right, so now what this will do is it'll just make it look different. I don't know how it'll look. I don't even know if it'll work. Well, I do, but you don't. But go ahead and do this and kind of see what happens once you do this. So you're multiplying here. And remember, when you do this, the middle term will cancel out. So really all you have to look at is the first and the last. All right, so go ahead and do this. Pause the video, try it, and then come back. All right, so when you do this, you would multiply the numerators. You'd have x plus 1 minus 1, which is really just x. And I'm going to rewrite this as the limit because we're going to try to plug it in. So it's going to be the limit as x approaches 0 of x over, and when you multiply these, you'd have x times the x plus 1. So x times the quantity of x plus 1 plus x. We could pull an x out there, but that's unnecessary at this point, because even here, when we try direct substitution, you would end up getting 0 over 0, which means we still can't do that. But now we don't have to rewrite it, we can simplify it. Because if you look at every single term, you have this term, and that term, they all have one thing in common. They all have x in common, which means we can take an x out. And when we do that, we factor an x out of everything, meaning if you factor an x out of the top and the bottom, they cancel out to be just 1. Our new function, we're going to write the limit as x approaches 0 of just 1 over the square root of x plus 1 plus 1. Now when we plug that in, you can actually plug it in. You'd have 1 over the square root of 0 plus 1, which is 1, plus 1, or 1/2. All right, so analytically, this is what it looks like. We can just make it look different. We can change it either by simplifying it or rewriting it in some other fashion. And now the very last thing for this video is looking at two limits that you must be familiar with. And in this class, we're not necessarily going to go over the proof of why these are true. If you look at the graphs, you can see that they're true. For example, the when the limit as x approaches 0, sine x over x, it's 1. right? But if you try to plug 0 in, it's undefined. But if you look at the graph, it's going to be 1. Also, 1 over cosine of x, 1 minus cosine of x over x, that is equal to 0. If you plug in 0 in, you see it's undefined. But just these you have to remember. Down here on the first one, we're going to try to get this one to look like sine of x over x. Go ahead and you're trying to get this one to look like that one. So go ahead and pause the video, try this on your own, see what you can come up with. Okay, and you notice we can't use direct substitution. So we know tangent is sine over cosine. In trig, you learn to manipulate functions and rewriting them using all of these identities, and the simplest one is sine over cosine. All right, so now we can rewrite this using a little bit of algebra. So you would have the sine of x over cosine of x times 1 over x. And even that one you can rewrite. Going to just remember I can multiply them in whatever order that I want to. So it's going to be sine of x over x times 1 over cosine of x. And if I look there, I have what I need, right? So I can take the limit as x approaches 0 of my sine of x over x times the limit as x approaches 0 of my 1 over cosine of x. Because I know that this right here, I know that that's going to be 1. And also I know that when I plug 0 in for your x right there, that is also 1, because the cosine of 0 is 1. And so you would have then 1 times 1, which is just 1. And that's our final answer right there. Let's do that again down here. And you're also going to be trying to use this first one of sine of x over x. This is a little unique. All right, see if you can't come up with a way to manipulate this. You'll have to change it a little bit to get it to look like the sine of x over x, because right now it doesn't look like that. Okay, to give you a hint, right, you could also rewrite this as the sine of f of x over f of x. X just is representative of some function, okay? And that would be equal to 1. Go ahead and try that one, this one right here, and then come back and see how you did. All right, so for this one, we're going to get to look like what we want it to look like, we're going to change this, and we're going to multiply it by 4. Because if we do that, now I can get this bottom function to look exactly like the function inside the sine, which is 4x, right? So now, if you think about this, you can rewrite this. We're going to do the limit as x approaches 0 of 4 times the limit as x approaches 0 of sine of, you could think of this as y over y, because it doesn't matter. No matter what that is inside there, it's always going to be 1, okay? So then the limit as x approaches 0 of 4, that's a constant. We learned earlier in these notes, that's just 4. Limit as x approaches 0 sine of y over y, we learned just now, that is equal to 1. And so our overall limit's just going to be 4. All right, so manipulation. Manipulate them to kind of get them so you can rewrite them and then find those limits analytically. All right, that is all that I have for this video. Let me scroll. And we're looking at evaluating limits analytically.